Look at this gear. It is solid, precise, and ready to be installed. But before a physical object like this ever touches an assembly line, it has to exist perfectly mapped out in a digital space. Over the next 6 minutes, we are going to build a functional mechanical part from scratch. We'll start with a blank digital canvas in Fusion 360 and turn it into a fully modeled, stress-tested, and manufacturing-ready component. To follow along, you need to download Fusion 360 from the Autodesk website, log into your account, and set up your workspace preferences. Specifically, choose whether you want to work in millimeters or inches. Establishing this accurate digital foundation allows you to catch measurement errors on a screen, reducing the risk of costly material waste on the shop floor. When you first open Fusion 360, step 1 is organizing your workspace. Click the Data panel in the upper left corner, select New Project, name your file, and hit Enter. Every 3D model starts as a flat outline. Click Create Sketch in the main toolbar and select the XY plane to give yourself a flat floor to draw on. Using line and circle tools, we map out the basic footprint of a bracket, drawing its raw geometric boundaries. To keep lines accurate, we apply constraints. By explicitly telling the software lines must remain parallel, the loose sketch snaps into a locked mathematical relationship. There is one crucial detail to check here. Make sure your lines connect seamlessly. A tiny, unnoticed gap breaks the shape and prevents the software from calculating the internal area. Once you have a constrained, perfectly closed 2D profile, your foundation is set. That flat shape acts as the strict genetic blueprint for the entire 3D model. With the flat sketch complete, we leave the 2D plane and step into 3-dimensional space. Select the Extrude tool and click your sketch. You type in your desired thickness and pull that flat profile straight up to create a solid block. For a symmetrical object like a pulley, we'd use the revolve tool around a central axis. Instead, our block has sharp corners, concentrating stress. We use the fillet tool to round outer edges and chamfer to carve structural bevels into bolt holes. Next, we activate the shell tool. This hollows out the interior of the part, leaving a uniform wall thickness that cuts down on heavy material weight without sacrificing the part's overall strength. This comparison highlights the progress. On the left is the raw shape we extruded, and on the right is our refined, detailed model. Applying these specific finishing features moves the design beyond a basic geometric block, preparing the model for the assembly and structural testing that follows. Mechanical parts rarely operate in isolation. To see how our bracket functions in a system, we switch over to the Assemble workspace. Using the Assemble menu, we can insert a secondary piece, like a connecting pin, directly into our current project file. To define how these pieces interact, we apply joints. We can snap the pin into the bracket using a rigid joint to lock it permanently, or a revolute joint if it needs to spin freely. Now that the assembly is built, we need to know if it will survive actual use. We transition to the simulation workspace to subject our model to virtual physical loads. This diagram shows exactly how stress distributes across the part under pressure. The cool blue zones are handling the load easily, but these bright red areas near the thin joints highlight dangerous stress points that could fracture. By isolating those weak points digitally, we can go back, thicken the joint, and secure a design that withstands the real-world forces it will face. With the design tested and proven, we navigate to our final environment, the manufacture workspace. Here, you prepare the part for production. You can generate automated toolpaths for a CNC machine, or save the geometry as an STL or G-code file for 3D printing. This final export process translates your digital geometry into explicit, real-world numerical coordinates that manufacturing hardware can execute. Your finished manufacturing file is now complete and sitting on your desktop. You send the code to your machine, and the hardware begins depositing physical material, matching your exact structural specifications layer by layer. We sketched a locked 2D profile, extruded it into a solid volume, ran the physics simulation, and exported the toolpaths. As you continue practicing, you can explore Autodesk's community resources to learn more advanced tools, like generative design, where the software calculates the optimal material shapes for you. Mastering these tools creates a reliable workflow for translating technical requirements into functional, manufactured hardware.